Hello guys, welcome to Self Help Maths Academy. Today, let us discuss the next part of diagonalization. Okay, so here we will we will first see what is the importance of this diagonalization. Okay, so basically we know that one important and interesting matrix. Say if A is diagonalizable, our matrix A, if it is diagonalizable, okay, then then if you want any power of the matrix, say in general a to the power k, we can write this as p d p inverse to the power k, because we can write when we are diagonalizing the given matrix, we can write our matrix A as p d p inverse. Suppose somebody asked you to uh, for example, to find out a to the power 100, where a is any matrix, a to the power 1000, any matrix in particularly, then do you think a will multiply 100 times? Not really. So if a is diagonalizable, then we can write our matrix A to the power k as p d p inverse to the power k. Then you may think that, mom, here it will be like, like we have to write the power of p, power of d, power of p inverse. No, not really. Using the properties of our matrix multiplication, we can simply write this as not to the power, it will reduce into p d to the power k p inverse. Okay, so this is simply, we will write this as p d to the power k and p inverse. Okay, so in short, we are actually like calculating just the d to the power k. So d is a diagonal matrix, it is simple to calculate, right? So hence we will not take the the power to the other matrices. For example, like say you have, let me tell you, if we have A is equal to PDP inverse. Okay, how do I write our A square? A square is A into A. So your A is PDP inverse. So we can write it as PDP inverse into PDP inverse, right? This is how we can write. So here, this is nothing but, now you see this into PD. I'll write this P inverse into P together. I'll write here D into P inverse. Alright. Now what you know that when a matrix multiplication, if its inverse is multiplied with it, you will be getting the identity matrix. So this will be your identity matrix, and when identity matrix multiplied with any matrix, it is the same matrix. So here you got D into D, which is D square, and P inverse as it is. This is your A square. Now when you want to write, for example, A cube, this is this is nothing but A square into A. So since already you have your P A square here, I can write this as P D square P inverse, and now I'll write my A as P D P inverse. So this is equal to, I'll write here P and D square as it is. I'll write my P square P inverse into P, because it is because of the associative property of the matrices, we can write them as a combinations. So again, P inverse into P is the identity matrix. When you multiply identity matrix with any matrix, it is the same matrix. So here I'll take D square into D, which is D cube. Okay, so this is your A cube. You observe now carefully. When you want A square, it is simply we are taking P D square P inverse. When you want A cube, it is P D cube P inverse. So in general, like this, when you continue, when you want A to the power k, it is simply P D to the power k P inverse. So this is the beauty of the diagonalization. So whenever you want any particular number, and you want to understand the power of that particular matrix, then simply we will calculate the power of D. And since D contains only diagonal elements, so power of D is easy, and we know the multiplication will be quite easy compared to like see for example any matrix, if you want to find out some matrix to the power 100 to some matrix to the power 95, so that will become quite easy by using the diagonalization process. So this is one of the interesting property. Okay, so now let me see one more example on the diagonalization. Before I continue, I think I need to give you some more ideas. For example, you have a matrix here. Let me take another example. When I was talking about the triangle, I mean like in diagonal, let me take the triangular matrix. Determine the following matrix if it is diagonalizable. If this is how they have given you, and the matrix A is given as say 5 minus 8 1 0 0 7 0 0 negative 2, if this is a given matrix. Okay, so I'll tell you, if without actually calculating, we can tell such kind of matrices when it is lower triangular or upper triangular matrix. Then if you see, since this is a triangular, I mean triangular matrix in particularly, it is a, if you observe, this matrix is a triangular matrix. Okay, so when I particularly tell you whether it is lower triangular or upper triangular. Here it is a upper triangular matrix. So here if you observe the diagonal elements, these entries are your diagonal entries. So this actually, in case of our triangular matrices, the diagonal elements will become its eigenvalues. So therefore the eigenvalues are here 5, 0 and negative 2. And since it is a 3 cross 3 matrix, we have got 3 eigenvalues, and here we have got all the eigenvalues are distinct. 5, 0, negative 2, they are distinct. So whenever you have a distinct eigenvalues, then that particular matrix will be diagonalizable. It is diagonalizable. Okay, so this is very important property. When you have the distinct eigenvalues, then it is diagonalizable. Okay, what about the matrices whose eigenvalues are not distinct? So sometimes, like that time you need to calculate, but whenever it is distinct, we are saying, we can say that it is diagonalizable. Okay, that is a property. So um and then, like for example, when it is like, when it is having a distinct eigenvalues, so again another property says, so the corresponding eigenvectors, for example, you have got say lambda 1 for a n cross n matrix. I'm talking about for a n cross n matrix. So you have got lambda 1, lambda 2 and so on up to say lambda, and these all are the distinct eigenvalues. You have distinct eigenvalues which are n eigenvalues. So corresponding to n eigenvalues, you have got n distinct eigenvectors. If you have got n distinct eigenvectors, okay, then those eigenvectors you will construct your matrix P. For example, I'll write here as v1 to vn. So these n distinct eigenvectors are say v1 to vn. Along with that, you will be constructing your matrix P. Then automatically your matrix P will be invertible. When I say, this is very important, okay, they are invertible because its columns are linearly independent. Linearly independent. Okay, so this is very important. Okay, whenever the eigenvalues are distinct, this is the important theorem we have to understand. Okay, so this is very very important and basic properties which we should know. And then now let us take another example where we will find out the diagonalization. Okay, whether we can find out the diagonalization or not. Let me take some 2 cross 2 matrix here. So if I have another example, we are taking a small example. So let our matrix A is equal to, we have 1 0 6 and negative 1. Okay, so this matrix is a triangular, so its eigenvalues are, if you see, it's a triangular matrix. If you see, it's a triangular matrix, you can see. So therefore the eigenvalues are 1 and negative 1. Okay, therefore you can say here without actually calculating, since it is a triangular matrix, it's a lower triangular matrix, so therefore the eigenvalues are 1 and negative 1. So now once you got the eigenvalues, find out the eigenvectors corresponding to those eigenvalues. So for lambda equal to 1, what happens to lambda equal to 1? You know that how do we find out? A x is equal to lambda x This implies ax minus lambda x equal to 0. This implies a minus lambda I times of x equal to 0. This implies your matrix should be a minus lambda I augment with 0. So in all this case, your lambda is equal to 1. So if I put lambda equal to 1, here it is simply a minus I augment with 0, right? So the matrix will be a minus I. This one we have to augment with 0. So therefore, this we will get as, since it's a 2 cross 2 matrix, so 1 minus 1. And this is 0 here, this is 6 here, this is minus 1 minus 1. Okay, this one we have to augment with 0. This is our matrix now. So here we will get this one as 0 0 0. This is 6 minus 2 0. Okay, so just we can like quickly do the R2 and R1 exchange. Then we will get here 6 minus 2 0 0 0 0. Okay, so simply we can write a solution. It is here, if you see, this is a free variable, so we can write this as 6x1 minus 2x2 equal to 0, and here your x2 is free. X2 is free, so here you can write 6x1 equal to 2x2, or dividing both the side by 6, you will get x1 as 1 by 3 times of x2, and your x2 is free. X2 is free. So when you write a solution, your x will be x1 x2. This is equal to, your x1 is given as 1 over 3 times of x2, and x2 is x2 because it is free. So you can write this as x2 into 1 over 3 1. So here this is your corresponding vector. Either you can multiply, if you take x2 as 3, okay, then if x2, if you multiply this, I mean, since x2 is free, right? So if I choose my x2 value as 3, multiply that with the inside value, inside vector, you will get here 1 when I multiply with 3. Okay, if your x2 is 3 in particularly, then this will be 3. So either you can take this as your vector, eigenvector, or you can take this one as your eigenvector, no problem. Okay, so with respect to, for lambda equal to 1, I am taking my eigenvector v1 as, say, 1 3. Okay, and similarly for lambda equal to, the next eigenvalue is lambda equal to -1. So same way, same equation I am taking, instead of lambda equal to 1, I am taking lambda equal to -1. So therefore this equation becomes for lambda equal to -1, same way you should do. I'll do it, redo it again. See, ax equal to lambda x. This implies ax minus lambda x equal to 0. This implies a minus lambda times of I times of x equal to 0. And the augmented matrix is simply a minus lambda I augment this with 0. This should be our matrix. So here I am saying my lambda is equal to -1. So just put for lambda equal to -1, this will become negative of negative, it is positive. I augment this with 0. Now we will write our matrix as, the given matrix as 1 plus 1, and this is 0. This is 6 minus 1 plus 1. This is 0 and this is 0. Okay. Now this is equal to, here what we get? We get here 2 0 0, and this is 6 0 0. Okay. Yeah. Now similarly, I use now the operation R2 changes to R2 minus 3 times of R1. Okay, since it is 6 and 2 there, so therefore it will be 2 0 0. This one is 0 0 0. Okay, so here simply what we do, we can write here 2x1 plus 0 into x2, which is equal to 0. Since your x2 is free, you can write here 2x1 equal to 0, and this gives you x1 equal to 0, and x2 is free. So therefore x2 is free, it's a free variable. So x is equal to x1 x2. Your x1 is 0, no problem. Okay, and x2 is x2. Okay, so therefore this you can write as 0 into x2, in fact, no problem. x2 if you take out, it is simply 0 and 1. So 0 and 1 will be your eigenvector 2. Okay. So therefore what we have got for lambda equal to -1, you have got 0 and 1. So therefore for lambda equal to -1, your eigenvector, let me take it as v2, that is 0 and 1. So now we have to construct our p. P is what? Yeah, as your choice of whether you take in v1, you can take first and v2 next, or v2 first and v1 next. It's up to you. So now I'll take my v1 first. Why v1 was I have chosen as 1 and 3, and v2 is 0 and 1. So this is our p. Now we constructed p. So similarly with the choice of p, we have to construct our d. So as you know, this you have chosen as lambda equal to, with this is corresponding to lambda equal to 1, this is corresponding to lambda equal to -1. So therefore d is, this is 1 and this is -1. Okay, 1 0 0 -1. So this is your d. So therefore you can just verify whether your a into p is equal to p into d or not. So your a is given as, your a you started with 1 0 6 -1, and you got your p as say 1 0 3 1. Let me multiply this. So this will be, you know that simply this into this. Here you are getting 1, this is 0, and this is 0 and 0. This is 6, sorry, 6 -3. This is 0 and -1. So here you will be getting answer as 1 0 3 -1. Okay, and similarly let us find out our p into d. So p is p into d. This is your a into p. Okay, so p into d is 1031 1031, and your d is 100 minus 1, sorry, it is 100 minus 1. So let us multiply this one. This will be now, this into this again. This is 1 plus 0, this is 0 plus 0, and this is 3 plus 0, this is 0 -1. So this will be again 1 0 3 -1. If you observe this and this matrix, they are one another same. Hence whatever we have calculated, our p and d, they are correct. Okay, so if in case they ask you p inverse, you have to find out p inverse also. Okay, with our usual method which we have discussed in our module 2, whether you can use the Kramer's rule, or you can use also the adjoint method, or if you want you can use the Jordan method to find the inverse. Okay, so that's how you can find out the diagonalization. All right, so now I think one example I'll give you. Just try it and answer me in the comments. So what you'll be getting the matrix, I mean, like, whether the given matrix is diagonalizable or not. I'll also give you here quickly the suppose -1 -3 -3 4 4 1 and -2 0 3. This is our given matrix with lambda equal to say 1 2 3. So these are our lambda values already given you. Okay, now you need to check whether the given matrix is diagonalizable, and also you have to check find the corresponding eigenvectors and the matrix p and d respectively, and you can answer me in the comments, and let me know what is the answers you're getting for this particular example. Okay, and I think you should comment your answers in the box about this particular matrix. Okay, that is one thing I have to tell you. And then let me take another one example. That is, say here they have given you the matrix as 4 2 2. Let me take this as A, and 2 4 2, and then we have given with 2 2 4, and lambda is equal to say 2 and 8. So these are the eigenvalues we have given with. Okay, so let us see how do we find out the, because now the step 1 is reduced, because we are not finding out the eigenvalue. We are already got the eigenvalues. The only thing we have to find out now the eigenvectors, corresponding eigenvectors, right? So let us find out the step number 2, finding the eigenvectors. Okay, for finding the eigenvectors, eigenvectors. So here let us start with the eigenvalue 2. Now for lambda equal to 2, you know, have this practice of writing, guys. So ax equal to lambda x, we know. This implies ax minus lambda x equal to 0. This implies a minus lambda times of I times of x equal to 0. This is nothing but your augmented matrix is a minus lambda I augment with 0. So now in this case my lambda is 2. So this gives you a minus 2I augmenting this with 0. So this is our matrix, right? Now let us convert our matrix into this. So a minus 2I will give you 4 minus 2, 2, 2. Then this is 2, 4 minus 2, 2. This is 2, 2, 4 minus 2, augmenting this with 0. Okay? Yeah. Now this will be equal to 2, 2, 2. Every, I think, row we are getting here 2, 2. It's a beautiful matrix. Okay. Do the row operation. So here the row operation will be R2 changes to R2 minus R1. R3 changes to R3 minus R1. Okay. So once we get this one, we will be having here 2, 2, 2, and this is 0 as I'm not doing any changes in R1. So but R2 and R3 are 0. And also what I can do is from R1, I can take this 2 out. So I will be getting simply 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0 and 0. Okay. So let us write this as a solution. If you take this as x1 plus x2 plus x3 equal to 0, your x2 is a free variable and x3 is a free variable. We can write this x1 as negative x2 minus negative x2 x3, and x2 is free here and x3 is free here. Okay. So now let us write this as a solution. If you write it as a solution, your x is equal to, okay, your x will be equal to x1, x2, x3. This is equal to, your x1 is negative x2, negative x3. x2 is x2 and x3 is x3. So this is equal to, okay, if I take x2 out, negative 1, 1, and there is no x2 term here in the last term, and x3 if I take out, here it is negative 1, 0, 1. Okay. So here this one is your v1, this one is your v2, corresponding to x2 and x3. We have got two particular vectors. So let me take for now lambda equal to 2, right? We have taken lambda equal to what? Lambda equal to 2. Yes. For lambda equal to 2, we have got our v1 as negative 1, 1, 0 and v2 as negative 1, 0, 1. So these are my two vectors, the beautiful vectors we have got. And now let us consider lambda equal to 8. For this, let us again start with the same equation. Ax is equal to lambda x. Why I'm writing it again? Because it will become a habit and practice for you when you're writing it. Okay. Then this will be like ax minus lambda x is equal to 0. This implies a minus lambda times of I into x equal to 0. Or when I am writing this as augmented matrix, it is simply this matrix. And in case of this, we have lambda as 8. So therefore my matrix will be a minus 8I augmenting this with 0. Okay. So now let's write this. This is equal to, this is now 4 minus 8. This is 2. This is 2. This is 2. Here 4 minus 8 and 2. This is 2, 2, 4 minus 8. Okay. This one we have to augment with 0. Yeah. So now we get here, this is negative 4, 2, 2, 2, negative 4, 2, 2, 2, negative 4. This is now 0, 0, 0. Okay. Yes. All right. Now since I think we can exchange R1 and R2. R1 and R2. Then we get here, this is 2 minus 4, 2. This is 0 here. This is minus 4, 2, 2, 0 here. This is 2, 2, negative 4, 0 here. Yes. Now, let me write R2 changes to R2 plus 2 times of R1. R3 changes to R3 minus R1. So, this will be equal to 2 minus 4, 2, and this is 0. Okay. Yeah, this is minus 4 plus 4 is 0. So here minus 4 plus 4 is 0. Then this is 2 minus 8, that is minus 6. 2 plus 4, that is 6 again, and this is 0. And then this will be like R3 minus 7, this is 0. Then this is 2 minus of minus plus 4, that is 6. Minus 4 minus 2, that is again minus 6, which is equal to 0. Yeah. Now it's a beautiful matrix again. R3 changes to R3 plus R2. Let us do that one. This will give you 2, negative 4, 2. This is 0 here. 0 minus 6, 6, 0. So this is when I add 6 minus 6, it is 0 and 0 and 0. Okay. Yeah. Then what we do is from R2, I think we can take that negative 1 by 6 out. Okay. Yeah. So this will give you 2 minus 4, 2. This is 0, 0, negative 1, 1, 0, 0, 0, 0, 0. Yes, this one. Now I think yeah, we are like using this R2, and we'll try to make our this element 0, or we can also make this element 0. Let's see, however, but I think R1 changes to R1. Yeah, let me make that element 0. Yeah, R1, or we can also make this element. Yeah, this also we can make 0. Let's see. I think this will become simple. R1 minus 2 times of R2. Let's try. This one will be equal to, this is 2, as we are not doing any changes here, it's 0. And then minus 4 plus 2 becomes minus 2 here. Minus 4 plus 2. So 2 minus 2, which is 0 again. This is 0, negative 1, 1. This is 0, 0, 0. And this is again 0, 0, 0. I think, yeah, it doesn't make much changes, but let's write now the solution. I think, and from R1, what I'll do, I'll just simply take this 1 by 2 from R1. We will get here 1, negative 1, 0, 0, 0, negative 1, 1, 0, 0, 0, 0, and 0. Okay. So now let us write a solution. So this will be equal to x1 minus x2 equal to 0. And here it is minus x2. Minus x2 plus x3 equal to 0. And from last it is 0 equal to 0 means x3 is basically free. So from here our x1 is x2. And from here your x2 will be equal to x3. Okay, because minus x2 is minus x3, so x2 will be equal to x3. So I can put my x2 value as x3 in this equation. So therefore your x1 will be equal to x3, and x2 is also equal to x3, and x3 is what? X3 is a free variable. So therefore when you want to write x, this is simply x1, x2, x3, and your x1 is x3, x2 is x3, and x3 itself is x3. So it is a beautiful vector 1, 1, 1. Okay, so therefore for lambda equal to 8, we have got our v3, because v1, v2 we already got it. So this is 1, 1, 1. Okay, now we have got what? We have got our v1 and we have got our v2. Alright, so now let us write the P, construction of P. So construction of P will be, now I'll take an order as V1, V2, V3. Okay, so I'll not be doing changes in the order. So here with respect to with respect to lambda equal to 2, lambda equal to 2, what are my eigenvalues? What are my eigenvalues here? Minus 1, 1, 0, minus 1, minus 1, 1, 0, and then you also have minus 1, 0, 1, I think, yeah, this one, minus 1, 0, 1. So this one is your eigenvalue, minus 1, 0, 1. And with respect to lambda equal to 8, this is the eigenvalue. So let us write this one. So whatever the order you are following, please be careful. There is here there is no condition that you should use 8 first, lambda equal to 8 or lambda equal to 2. But the condition is on the D. Whatever the order we are following here, we will follow there also. So since this is corresponding to lambda equal to 2, this is corresponding to lambda equal to 2, therefore our the diagonal matrix should be here 2, 0, 0, 0, 2, 0, because this is with respect to 2 and this is also with respect to 2. So then 0, 0, the last one is with respect to 8. So this should be your diagonal value. Okay, for example, if you take your P as, let me write it here. If you take your P as first V3 and then V1, V2, then your D must be your D construction must be what? Because your V3 is with respect to 8, first 8 will come and then your 2. Okay, so this is how it should be. If you follow this one, then this must be your D. If you follow this one, then this must be your D. All right. So this is what you have to keep. This is very important step. You can say it's a critical step. All right. So now clearly you've got your P and you've got your D. So I think I'll leave you for checking whether A into P is equal to P into D. It holds or not. Definitely it will hold, and you just check it. Okay. As I told you, it's a good habit to check whether it is whether we are getting the correct answer or not. And if in case if they ask you to find out P inverse, so I think what I'll suggest you is, now I've already given you the P value, so use the Jordan method, which we already know how to find out the inverse by using the Jordan method, and you will find out the inverse by using the Jordan method. Okay, I'll just give you the answer for your P inverse. Just verify your answers, guys, for P inverse by using the Jordan method. I think, hope you remember, we write our matrix P when you want to find out the P inverse, you will write your matrix, given matrix, this one, augment this with the identity matrix, and try to this matrix P you will augment with the identity matrix and do the row operations in such a way that this P should convert into I, and here whatever you're getting after doing all these row operations, this will be your P inverse. So that is your Jordan method. So I think you will do that. I'll give you the direct answer here. Just verify your answers, guys. Okay, and comment me in the box whether you got the same answer or different answers. That I think we have to note. So it's very important to, because you have studied your Jordan method, I think, in the first module, so but you're using that very method in the fifth module. So therefore I told you all the modules are connected, guys. Okay, so yeah, so this is the answer you should get. So just check your PDP inverse. All right. Okay, then I think with this, let me conclude today's discussion. Maybe in the next class, we will see some more interesting concepts and some other interesting, ideas with respect to different concepts. Okay, then till then, take care, guys.